two-thirds, 60% roughly, because of the energy. If we change energy, we change also the probability. So it was 1/3 once and 2/3 in the other case. This is E and L are the experimental parameter. The fundamental parameter here are the difference in mass and the mixing angle. So we know that actually we have three kinds of neutrino, E, mu, and tau, and we have to replace the 2x2 matrix by a matrix of 3x3. This is the analogous of the Kabib-Kobayashi-Maskawa matrix, and the name is macchina che fa scata. Ponte Corvo is here because it was the first that postulated that neutrino undergo oscillation. So I do not want to spend a lot of time about mixing. I have simply to stress that, as I said before, is oscillation in vacuum. We have to take into account that you have also oscillation in matter. Neutrinos are created at the core of the center, at the core of the sun, in the center, and when the neutrino have to go from the center to the outer space, you have to traverse the solar medium. Solar medium is made from electron up and down quark, so there is a difference between electron neutrino and the other kind of neutrino, because both neutrino, E, mu, and tau, neutrino, undergo neutral current in the same way, but electron neutrino can also interact via scattering. For this reason, we have to replace, in the case of a medium, the probability introducing this number, that is the electron density. The density inside the sun is roughly at the center 150 gram per square centimeter, per cubic centimeter. So, beside the other detector at the beginning of 2000, another observatory began to take data. It was the Southern Observatory. Southern is a mine located in Ontario, Canada. And the particularity of this detector is that is composed by 1,000 tons of heavy water. So you have the same reaction that Super K and Kamiokande had, because you have water, so you are able to see the scattering on electron. But the fact that you have deuteron, you are able to see this kind of reaction. So the first one is the same that Kamiokande. Neutrino of all type, X, with X I mean mu, tau, or E, and it goes this reaction. But if you have all type of neutrino impinging off a deuteron, you can split the deuteron that is composed, as I said before, with the proton and neutron. Or in the case you have an electron neutrino, not only you split the deuterium, but you convert the neutron into proton. So, if you compare the flux, because you can see all these reactions independently, you can, for example, here is plotted the flux in the case of electron is the CC reaction, and you see this number in terms of 10 to 6 neutrino per square centimeter per second. If you look at the flux for mu and tau means flux of NC minus CC, you see that the best value you obtain is this number. I mean, you see how many neutrino are come. Okay, I can write it this way, it's better. Okay. Suppose that I have 100 electron neutrino coming from the sun. Only electron neutrino, because there are proton-proton reaction. Suppose that 50 of them, half of them, convert into mu or tau. Okay, and tau neutrino. Now, if you are sensitive to this reaction, and see, you see, okay, at the beginning you have 100 electron neutrino. in your detector you have 50 electron neutrino plus 15 non-electron neutrino. Okay? So if you are able to see all the neutrino, you count 100. If you are sensitive only to electron neutrino, you count only 50. Okay? Now, there is also this reaction, the elastic scattering. And in the case of the elastic scattering, I have to say that the cross section, okay, also mu and tau neutrino undergo elastic scattering, but the cross section is 1/5 smaller than the electron neutrino. So, if you look at this reaction, you see 50 electron neutrino, the survived electron neutrino, plus the other, but with a cross section that is 5 times smaller. So the other 50, you see 1/5 of 50 means 10. So you see 50 plus 10. This is why in elastic scattering you see more events than CC reaction. Okay? So if you compare the Phi-CC reaction over the Phi-NC reaction, you have directly the probability, the survival probability of the electron. This means that 35% is, are survived. The other one has been converted into neutrino. So this is the very proof that the neutrino actually transform from electron neutrino to another kind of neutrino. And this is why the detector constructed in the past so less neutrino than okay. This is the summary of all neutrino. I added to the trick, this is some stakes, Kamiokande, water, gallium, and here are Sudbury in the case of chemistry, only 35%. In the case of all neutrino and C reaction, you see that is similar to the predicted one. Okay, so the solar standard model is correct. The best value for what concern the difference curve in masses and the mixing angle are this one. Beside the solar neutrino detector was built another detector that is Kamlan, located in Japan, that was looking for anti-neutrino coming from reactors. And it was sensitive to these parameters, and also the detector confirmed that actually neutrino oscillate with these parameters. Right? This is another proof, indirect proof, because you employ another kind of source, and other reactor power from Japan and Korea, and with a distance of the order of 180 kilometers. So this was the situation. Now, I want to speak about the Borexino detector, located at the Laboratorio Nazionale del Sasso near Rome. Rome is here in the center of Italy. This is a sketch of the apparatus. This is actually Borexino. This is the plants that we will show later on. And this is the counting test facility. Small Borexino, if you want, in order to prove the feasibility of the detector. This is the underground laboratory, and all the plans are located in Hall C. So why is important Borexino? I apologize. Okay, in any case, this is the same energy I wrote before. For what concern Sudbury, the last detector we saw, and the Super Kamiokande, we see only the very last part. I mean, from here, roughly. The threshold is quite high, is on the order of 5, 6 MeV. This means about here. This is logarithmic. You see only this part in real time. For what concern the lower part, this one, from 862 kV, the threshold of mistake, you are able only to integrate